Hey guys, so today we're going to go over some inverse trig intervals. Okay, so I can't go over all of the different examples that we've gone over in class because that would mean like a 2-hour video, but these are your general integral rules for sine, tangent, and secant. So we will explore these on the next couple slides. Okay, so we'll start with something that's relatively simple. And also I would recommend that you have your notes out while you do this so you can remember the forms for sine, secant, and tangent. So upon first glance, this looks like similar to a sine problem. And if you'll remember, the integral for that would be dx 1 minus x squared. And, you know, in the previous slide, they were used, doesn't matter, same thing. And also note that, you know how it was just like, you know, a squared and u squared? That's just giving like the general form. So, you know, it doesn't really matter like what this is in the beginning, but you always want to get it to 1, which leads us to our first step. So this 9, therefore, we want to get it into a 1. Well, how do we do that? Well, obviously, you have to multiply through by 1 over 9. But it's in a square root, so therefore you have to multiply by square root of 1 over 9, and then on top you have to multiply, on top, numerator, whatever, multiply by 1/3. Same thing, but it's easier to go by like this. And so we're going to take the 1/3 and put it outside of the integral because you don't really want to deal with fractions right away. So integral dx. So we multiplied through by the square root of 1 over 9, so that becomes 1 minus x squared over 9. Except you want this whole term to, well, you want the whole thing to be squared. So therefore, I'm going to rewrite it again. So integral dx 1 minus x over 3 squared. Because when you square it, you get x squared over 9. And it's now that this matches the form for sine. So therefore, you can write it as in the sine, the inverse sine, or alternatively, arc sine, same thing, of x over 3, and then plus your constant. And the 1/3 is already there because notice, like when you take the derivative of the x over 3, that the derivative there is 1 over 3, but we already have it over here. So you're good with either of these two answers. Okay, so next let's look at this one. So this one is obviously going to be a secant one because if you recall, what makes that unique is that the x term will be here, or the square term will be there, and then there will be a single x term here. So we know that the secant is written as dx x square root of x squared minus 1. So this is the term where it basically just means that there's something squared. So if we go back over here, we realize that it's a 2x squared because 4x squared, or rather 2x to the second power is 4x squared. And then dx here. But you'll notice that, so if your x term here is 2x, not that they're the same thing, but just like this term right here is equivalent to this term, the derivative of the 2x would be a 2, which means that technically there should be a 2 in the numerator. But the fact that the x is here, and that we know that the x in this problem would be 2x, technically there's like a ghost 2 here and a ghost 2 here, but we would know that those would have canceled out like when you did the derivative. So therefore you just write it as the inverse secant of 2x plus c, or alternatively arc secant 2x plus c. Okay, so now let's look at this one with trig. It looks complicated, but it's basically like in the same form as one of our trig expressions. And if you were to look at this, you would probably see that it matches most closely the expression for the inverse sine, because the x term is here, and we notice that the derivative of tangent, is secant squared of x. But we want to get a 1 where the 25 is, because that is the form of the secant. So therefore you have to multiply by the square root of 1 over 25. Sorry, it's getting kind of messy over here. And then 1 over 5, because as we know, the square root of 1 over 25 and 1/5 are the same thing. So we're going to bring the 1/5 out to the outside. So then the integral of secant squared, secant x squared, whatever you say it, square root 1 minus tangent squared x over 25 dx. But there's a bit of an issue there because, this is the whole squared term. So it's going to be 1/5 secant squared of x, 1 minus the tangent of x over 5 squared dx. And you could do this with the u substitution, like you could make, tangent of x your substitution. I'm not doing that here because if the derivative is like so obviously in the problem, how secant squared is the derivative of tangent squared, then, or rather just tangent, then it's not really necessary, but you could do it with u substitution. So seeing as our u value would be the tangent of x over 5, as we see here, you're going to write it as sine, or rather inverse sine, tangent of x over 5 plus c. And the 1/5 doesn't really have a consequence because notice, like, when you take the derivative of tangent x over 5, it would be secant squared of x, but you have the 1 over 5, so that would just transfer out. So you don't have to multiply through by anything. And yeah, I just realized that it's probably easier to do it with the u substitution, at least for most people, so I'm just going to do it on the next slide. So sorry if this got scary. Yeah, so when you use the u substitution, we're going to go with u equals the tangent of x. So then du is equal to the secant squared of x dx, and then dx is equal to du over the secant squared of x. So therefore you can write it, so integral, that looks like an S, my apologies, secant squared of x over 25 minus u squared, and then du over secant squared x, out. So the integral of du over 25 minus u squared. But we know to match the, the sign form, this has to be 1, so as we did on the previous slide, 1 over, or square root of 1 over 25 over 1/5, so 1/5 integral du, or rather, just got to erase that, 1 minus u squared over 25, but we know that the u squared over 25 becomes u over 5 squared. It's now in the form that we need, so we know that it will be, so it'll be inverse sine of u over 5 plus c, except for the u is tangent of x, so you would just write it as the inverse sine of tangent of x over 5 plus c. Okay, so this one's a little more complicated because it would include 2 operations, both natural log and an inverse trig problem, but we can get through it. So I'm going to start by splitting up the integral. So it's going to read as x over x squared plus 1 minus the integral of 3 x squared plus 1. Sorry, dx and then dx here. Okay. So for this first part here, we're going to, if you can see it, then just write it out how you want to, but if you want to do a u substitution, you could do u equals x squared plus 1, du equals 2x dx, so dx equals du over 2x, and then integral that, not that that's a verb, but x over u, and then u 2x, x's are gone, take out the 1/2, becomes this, so du, gotta zoom out a little bit, Well, that's cool. Okay, and then you know that the integral of du over u is just the natural log of u, but u was x squared plus 1, so it's going to be 1/2 the natural log of x squared plus 1, and we know that x squared plus 1 is always going to be positive because the squared would negate any negatives, so this is the answer for your first part. But over here we have the inverse trig. And it might be a little easier to spot if you take out the 3, so or rather factor out the 3. So it should be minus 3 integral 1 over x squared plus 1 dx. And when you do that, you're probably going to see that it matches the pattern for a tangent problem. So it's going to be minus 3 inverse tangent of x. So then you have this part and then this part. So we're going to put those together and write 1/2 the natural, or rather absolute value of x squared plus 1 minus 3 is the inverse tangent of x plus a constant. So for this last one, we're going to do something that's slightly more complicated. I don't know if this is going to come up on the test, but safe bet, because I think it was in the homework. But anyway, so you know how he talks about, like you have to take the road traveled or whatever, use substitution. If that doesn't work, then don't use it. Experimentation. This is kind of experimentation. I have the work for it, but if you come across a problem like this, try and split it up and see where it takes you. So first, I would do this. So this is x plus 5, but I kind of want to make this look like x minus 3. So how about we split it up? So integral x minus 3, 9 minus x minus 3 squared dx plus the integral of 8 over the same thing from before. Dx. Now, as it turns out, this one will just end up being quite simple, and then this one will be inverse trig. And you can usually identify that by like the difference between the number in the parentheses and the in the numerator. So, like we see here that this is a variable, and you know that since this is also a variable that well, and also just because you see it, that the top part is not going to be the derivative of this part, so therefore it can't be inverse trig. But up here it's a constant, so we can fool around with the constants a little bit to make it into the derivative. So it might help this one over here if you were to write it like x minus 3 times the quantity of 9 minus x minus 3 to the negative 1/2 dx. Because in that case, all you have to do is up the power. For integral, you go up. So 9 minus x minus 3, sorry, this should be squared. Squared to the 1/2 power. And you would have to notice that when you take the derivative of the outside, this 1/2 would move down, but so would this too, so those would cancel out. So therefore there's no need to put a constant there. And then the negative will also carry over. So your final answer for the part 1 of this integral would be 9 minus the quantity of x minus 3 squared. And you can do a square root of that, or you can do to the 1/2 power. I'm just going to write it as square root. So that part's done. And now we go over to what we think is the trig. So we're going to do what we've been doing. So we already have a term here that conforms to the like you need like a 1 minus something squared rule, because this is looking an awful lot like a sign problem. So the x minus 3 is good. However, that 9 is bothering us, so we are going to multiply through by, I'm going to do this in, let's do it in green, square root of 1 over 9, and then 1/3 because of the same thing as usual. So let's take out the 8 thirds, so that's going to be plus 8 thirds the integral dx square root of 1 minus, and then since we know that, you know, x minus 3 quantity squared over 9 is the same thing as x minus 3 over 3, as we've been doing, because once you square it, the 3 becomes a 9. So we're going to leave it like that. And once again, if you see it right away, you don't have to do a substitution for u, but you know, if you want to, you can do this. So u equals x minus 3 over 3. Du equals dx over 3, or 1/3 dx. So then dx is equal to 3 du. So once we plug that stuff in, you get plus 8/3 times the integral, and then dx is 3 du, 1 minus u squared. So the 3's are gone, so we have plus 8 integral du, 1 minus u squared. And we can see now it's the perfect setup for inverse sine. So it's going to be plus 8 inverse sine of u. However, u is x minus 3 over 3. So it's going to be plus 8 times the inverse sine of, what was it, x minus 3 over 3. So therefore, for this part, we have this answer. And then for the top part, wow, this is going low, we have this part. So put those two together, you get the square root of 9 minus x minus 3 squared. And, sorry, that should be a negative there. Plus 8 inverse sine of x minus 3 over 3 plus your constant. So that is your final answer. If you have any more questions about integrals, please feel free to ask me or another member of the math team. Thank you.